Okay, so now we're looking at this problem. The two slender bars, each of mass m and length b, are pinned together and move in the vertical plane. If the bars are released from rest in the position shown and move together under the action of a couple m of constant magnitude applied to AB, determine the velocity of A as it strikes O. Okay, very well. So just looking at the geometry of the problem here, um, we notice that, well, this angle is theta, and this angle, I can even look at the bigger one just to be looking at the same reference for both of them. This angle is pi by 2 plus theta, and this angle is pi by 2 minus theta. So if I look at omega OA, I can write this as the derivative of this angle, which becomes theta dot Ez. And if I look at the angular velocity of length AB, again I can write it as the derivative of some angle measured from a fixed reference. So this line, it's the derivative of this angle, so I can write it as minus theta dot Ez. So the two bars throughout the motion, due to the isosceles kind of triangle here, are going to have the same angular velocities but with opposite signs. I tried to solve this problem a lot preparing for this video, and for now, we're gonna try to solve it using the work energy theorem and see if it works. Well, this is a system of two bars. We're gonna write the work energy theorem of each bar and then sum them. That's how we do the work energy theorem for a system. We did the same thing for a system of particles. You find the work energy theorem for each particle and then you sum. So now if I'm looking at each bar on its own, let me draw the free body diagram of each bar. So this is kind of a bar. Oops, yeah, and this is another bar. We have the points A, B, B again, and O. I'll need to apply the weights at the center of masses, so maybe I'll call this C1, C2. That's for bar 1 and bar 2. I have the normal force at A, weight here, 1, a reaction force at B, and its opposite on the other side, action reaction kind of thing, W2, and reaction force at O. One more thing, we have the couple moment applied at this bar. The actual location of the applied couple does not matter. So now we can write the work energy theorem for each bar. So for bar 1, I can write that TB minus TA. So A is the initial state, and the system starts from rest. TA is equal to 0. Is equal, so TB minus TA is equal to the work of NA plus the work of M plus the work of W1 plus the work of RB. Very well. So the work of NA, that's the integral of NA dot VA dt, and we notice that NA is along EY, VA is along EX, hence this dot product is 0 and the work of the normal force is 0. The work of the moment is the integral of M dot omega dt from TA to TB, which I can write as the integral of m d theta. Well, that's because, let me do it step by step, that's m easy dot, well, in this case it's minus theta dot e z, that's omega dt, and that's minus m theta dot dt integral. I can write theta dot dt as d theta, so now the integral is minus m d theta from theta at a minus theta at 0. So theta at a is the theta that's given, so m theta tilde, kind of to just change the value 0 minus, so that's minus m 0 minus theta, so m theta. Very well. The work of the weight is gonna be negative because the center of mass is kind of lifting up. So that's mg yb minus ya. Here this is my basis, ex, ey. So yb, that's b cosine theta, sorry, b over 2, minus b over 2. Let me double check, this is indeed negative, so I think I have this right. And the last term, the work of RB, we just cannot calculate because we do not know the speed of VB. RB is changing in time. Nothing is conservative here. So we'll keep it for now. Okay, very well. Now let's write the work energy theorem for the second bar. TB2 minus TA2 is equal to the work of the the reaction force at O, plus the work of W2 plus the work of the minus RB, this minus RB force. So the work of RO is 0 for the reason that VO is 0. So that's RO dot VO, and VO is 0. The work of the weight is the same as for bar 1. The two have the same masses, and the center of mass has the same vertical displacement. And the integral, the work of minus RB is the integral of minus RB dot VB dt. And now we notice, well, if I want to keep the same color scheme, I should draw this in purple. Well, whatever. Minus integral of RB dot VB dt, that these two terms are the same. So when I sum the two work energy theorems, these two terms were cancelled out, which is awesome because I didn't know them, they were unknown. So 1 plus 2, system starts from rest, TB1 plus TB2 is equal to twice that work of the weight plus the work of the moment. The work of RB cancels out. Okay, awesome. Now what we need to do is we need to calculate the kinetic energies of the system at state B. And I'm just kind of reminding myself, what do we need to find here? We need to find the velocity of A as it strikes O. Okay. 1. The kinetic energy of the second bar endures fixed point rotation. So I can write the kinetic energy of it as TB2 is half I, so it's basically half HO dot omega, which simplifies to half 1/3 mb squared times theta dot squared at time B. Okay, now TB1 does not have a fixed point, so we're gonna have to write its kinetic energy as half mvc2 dot vc2, the center of mass, plus half hc dot omega, and this hc dot omega I can write it as half 1/12 mb squared theta dot b squared also. Now I have one equation, this one, and the unknowns are theta dot b and vc. Maybe I can find a vc in terms of theta dot b from kinematics. So let us try. We have that, well, we can write that vc minus va, vc1 minus va. Okay, I actually made a mistake here. That's 1. Okay. VC1 minus VA is equal to omega AB plus RC1 minus RA. Okay. VC1 we need to find, that's VA along EX. And omega AB we said is equal to minus theta dot EZ, and we're looking at instant 2 when RC minus RA is just vertical. So VA EX minus plus B over 2 theta dot B EX. Okay, so now I have this unknown VA. VC1 is VA plus B over 2 theta dot B EX. Okay, so now if I replace the equation, in the equation initial one, I will get half M VA plus B over 2 theta dot B squared plus 1 over 2 times 1 over 12 M B squared theta dot B squared plus 1 over 2 1 over 3 M B squared theta dot B squared is equal to 2mg B over 2 cosine theta minus B over 2 plus m theta. So again, we did the work energy theorem for each bar, and we summed the two work energy theorems. We calculated the kinetic energy of each bar, or at least expressions for the kinetic energy of each bar, and we got this equation, which contains two unknowns, VA that we need to solve for, but also contains this other unknown theta dot B that occurs multiple times. This theta is the initial angle theta, so we know it. So maybe we'll read the given and see if there's another way kind of to solve our dilemma here of one equation and two unknowns. Okay, I'm not really sure what to do. It might be that as the A strikes B, theta dot is 0. I'm not sure. I'll think about it and I'll get back to you then. Part 2 of this video.